Okay, so I'm going to take up a little bit of your time and talk about tracing a DNS reflection attack via anycast routing changes. So first, some history. First, there was the Big Bang, then the Earth cooled. This is on logarithmic time, by the way. So there was the Big Bang, the Earth cooled, TCP IP was invented, DNS was invented, and then people realized that it makes a great system for launching DDoS attacks. And that's why we're here today. So just to be clear, this is the kind of attack that I'm talking about, where there's a bad guy who can spoof packets and he sends them to some authoritative name server, and that name server sends a response to the victim. Some particulars about the attacks that I'm talking about now. These are occasional attacks that were reflecting off of the root name servers beginning sometime in early 2010 and continuing for quite a while, for most of that year. Typical load of this attack when it started was about 6,000 queries per second, and towards the end of the year it was higher. It was about 15,000 queries per second. So as a comparison, each letter of the root server system typically sees between 10 to 30,000 queries per second during normal operations. These attacks would tend to last for 1 or 2 days, sometimes less, not often longer. And one sort of distinguishing characteristic was that the query names in the attacks was always the same or very consistent. So normally it's really hard to get good data out of the root servers, but as luck would have it, at this time we were going through the DERS deployment, adding DNSSEC to the root zone, and there were sort of about every 3 weeks there would be a new incremental deployment, and all the root server operators would do another data collection, and they were uploading all of that data to DNS OARC. So that data is there at OARC, and that's the data that I analyzed for this. It's actually quite a lot of data. Each one of these little charts here represents one data collection period from the root server letters that are shown on the y-axis here. So there were about, let's see, I think there were 8 or 9 separate data collection periods. Some of the letters were better at participating than others, but it was really quite a lot of data to go through. So, to get a handle on this, what I did was went through all that data that we had and extracted the queries that ended with these 2 names that we saw in the attack traffic. So they've been somewhat anonymized here, but all of the queries ended with one of 2 second-level domain names. So to do that, I used this program called DNSCap, which can filter on names, and this process took quite a long time. One reason is just because I just sort of started it and let it run for as long as it would run, and luckily, the server stayed up for many months, and eventually it finished, and then I got around to actually looking at the data. There's a little, at the bottom of this slide, there's a little extract of how the queries would look in TCP dump. So the next step was to put all of those queries into an SQL database. Here's an exciting SQL table, just to show you that I'm serious about SQL. I'm not joking about that. And so from this SQL database, then I could run a number of SQL queries to sort of look at the data in different ways. So I defined an attack event as when the start of an event is when at least one name server sees at least 50 queries per second for either of these 2 names. And it ends when none of them see that level of traffic. And if there's a gap of 5 minutes or more, I say that's the start of a new attack event. So there were different numbers of attack events in the different data collection periods. You can see, for example, on March 23rd, there were 4 different attack events. And actually another definition of an attack event was the second level domain had to be the same. So there's two names in there, and I think I separated name 1 and name 2 into two separate events if they happen to occur simultaneously. Here's a graph that shows the traffic levels during one of the attacks. So this was an early one in January, and you can see that it's pretty flat, pretty consistent at about 6,500 queries per second. And all of the, almost all of the root server letters that we have data for are at the very top there. You can see this blue one here. This is actually JRoot, and this does not represent a loss of service, but it represents a loss of collection, a loss of data collection. So what likely happened here was the site where the data was being collected, this attack caused the disks to fill up, and then no more data could be collected after that time. So for the most part, it's flat. There's a few dips here and there, of course. Here's another look at that same event. So for each of these, I went through and just detailed the start time, the stop time, the maximum and the mean query rates, the names that were seen. In all cases, these were all queries of type 1. These were all A queries. And I listed the source addresses that we saw. And the source addresses were always kind of like this, between 1 and 5 unique sources. We assume that they're spoofed. Some sources were a little bit more popular than others for whatever reason. And between attack events, the sources tended to change. So there was not a lot of consistency in the sources between attacks. However, there was a lot of consistency in the servers that were being hit during the attacks. So this table here shows these are actually the server and the node names that we used at OARC when collecting the data, and the node names or the site names tend to encode their location. There's a lot of airport codes in here like JFK and LGA, LaGuardia, and so on. There's Miami. So these happen to be very consistent over time. For each event, we would always see iRoot's traffic at the Washington node and JRoot's traffic at the Bombay node, and so on. I think I already said everything on this slide. So this particular attack was a little bit different. It's perhaps not immediately obvious from this slide why it's different, but it has to do with what's going on here in this region. There's a number of sort of stalactites, if you will, of drops, and this is the list of the servers that saw traffic during this attack event. And one of the really interesting things was that for the first time in this event, we saw traffic at sites that we had never seen before. So for F, there was some traffic at the Amsterdam node. For J, there was, I forget what JSU is now, San Juan maybe. For K-Root, there was traffic at their Lynx node, and for L-Root, there was traffic at their Los Angeles node. So that this is something that's pretty interesting. And this graph shows sort of zoomed in time where the traffic for each server was hitting. And you can see, for example, like on this line for K-Root, it was going along at the normal location, which was I believe Napa of the Americas, and then bopped up to Lynx and then down back to the Napa Americas and did this. And for all of the sites, for all the servers that saw a traffic shift, they all shifted at the exact same time, these sort of 3 events. So this seems to be some kind of glitch in where traffic to Anycast-enabled servers shifted at exactly the same time on these 3 or 4 sites. So this seems to be some kind of routing problem, and since it affected everybody at the same time, we assume that it happened close to the real source of the traffic. So the hypothesis as well, perhaps the normal traffic was affected in exactly the same way. Here's a cartoon sort of, showing the idea here. There was perhaps a disrupted BGP session that caused that traffic to not go there, and then it shifted to these other 3 sites for those Anycast root servers. So I made a sort of a fingerprint of the times when the traffic shifted and which servers it shifted to. Here's the table for, again, this is for froot. So at these times, the from and to columns, these times the traffic went to this node and then to this node and flipped back and forth. And so by looking for real traffic that shifted in the exact same way, it came up with this list of IP addresses. So all of these addresses for these 3 root servers shifted at exactly the same time in the same way. So it turns out almost all of those addresses fall within these 6 or so net blocks, which are announced by AS21788. Here's the whois record for this for those networks. This is I don't know if anyone is familiar with this company or this ISP, but they're also known as BurstNet, and they're a company that sort of specializes in hosting and virtual services and that kind of thing. So, and another thing that sort of makes sense here is that this company is located in the U.S. East Coast, which makes sense sort of Anycast-wise that that traffic would be hitting root servers on the U.S. East Coast and in Europe. So to take this a step further, I wanted sort of more confirmation and went back through the other attack events to see if the traffic from AS21788 always hit the same nodes as the attack traffic was hitting. So it was, it's nearly 100% match. I have a bunch of boring, tables that show. In almost all cases, it was 100%. So, it seems that this routing glitch, which feels to me like, maybe the attacker kind of inflicted upon themselves by sending so much traffic through their ISP's router, caused a BGP session to reset, sort of outed them, if you will, as to their location. But the reason that this was kind of possible was because the root servers, it's a very diverse set of servers all around the world, and lots of different organizations involved in running those servers, and lots of Anycast, obviously. And of course, the other thing that really enabled this to happen was the massive amount of data that we just happened to be collecting at the same time. It has been asked of me, is this something that we could do in real time? Maybe if you had, enough machines and to throw at it, but you would really need some way to, I guess, to force these BGP sessions to be reset, and you would need something like the root servers, a very diverse set of Anycast sites, I think, to be able to see it. Any questions that I can answer about this for anybody?
Hi, Matt Poundstead from Affiliates. Your last couple of statements there, you're saying you'd kind of need more routing glitches in order to try and do this in real time, but that tipped you off to what was going on, but if you had enough data, wouldn't you be able to just do that with normal traffic without the routing glitch? Just find all the sources that are always talking to the same servers as your attack traffic, and I mean, it wouldn't be quite as good because you'd have some false positives in there, but it might help narrow it down a lot where the potential sources are.
Yeah, and I think that was kind of my plan when I started out with this, and stumbling upon this glitch was kind of lucky, But I think you're right. I think you could attempt something like that where you'd try to match a much broader set.
It might at least give you 10 or 15 knocks you have to call to say, have you got a ridiculous amount of traffic coming out towards this sort of thing, rather than
Right. I think so. Yeah.
John Christoph, Team Carmi, just to follow up on Matt's comment, I guess you could try to triangulate doing some trickery with your own announcements, or if not just you, maybe a collaboration between the routes or whoever's involved in this, by either removing your routes or adjusting your peering and so forth, and maybe announcing certain suspect ASNs so they see a loop and then they do something else perhaps. So something perhaps.
Yeah,
think it out,
I
right?
think so. I think I'm not enough of a routing expert to say, so I would rely on others to tell me what to put in the router config to do that.
Kyle Kreitz, Merit Network. I was curious if you were only examining A records, or if, because aren't text records usually used in reflection of text rather than A records?
That's true. We were collecting all the records, and this attack traffic was only using A queries for whatever reason. I don't know. Yeah, this doesn't seem to be a case where they were relying on the size of the response, but maybe just more on the volume of the response traffic.